So today is going to be the last day of us doing new stuff. I'm just going to do it up here. So today we're going to continue with integration by parts. And then what we'll do then starting Monday is we're going to begin reviewing for the AP exam. And we're not officially, some of you might remember I talked about how we were going to be doing 3 weeks of quizzes. Those don't actually start Monday or Tuesday. Thursday next week, I'll double check with Mr. Geisfeld, but I'm pretty certain this is what we had agreed upon. And so what we're going to do then, Monday, I'm going to find a bunch of either practice AP exams or maybe I'll even find some of the past AP exams. Right now, I'm working on the 2019 practice exam, which technically is this year's. And anyway, I'm thinking maybe that's one that I will give all of you, and we're just going to work on that Monday, Tuesday, Wednesday. Thursday then is when we're going to have our first assignment, and I'm not entirely sure yet if we'll start right with the Barron's book or if we will use another practice exam for that. And then on Friday, our first quiz, and then we're just going to be doing pretty much a quiz every single day for 3 weeks straight. So there's not going to be a lot of teaching for me. I know some people wanted us to go over the mock AP. I think Monday would be a good day for me also if you still have questions from the mock AP that I could talk about it then. And I think what I want to do too is I want to point out a bunch of questions that are going to be really important for review. Mr. Geisfeld and I know that the AP exam uses a lot of the same questions every single year. They change the numbers, they change the context. You've heard me say many times before, sometimes it's bees entering and leaving a beehive. Sometimes it's cars going in and out of a parking lot. Sometimes it's people going in and out of a mall. But it's basically the same question every single year, just with different things entering and leaving. So we kind of have an idea of what may be asked on the AP exam. At the same time, I'm a little cautious of just saying, hey, it's probably going to be this question, so we're going to do nothing but that. So I'm going to make sure that there's a good variety so we can address pretty much anything that could possibly happen. Okay, so that was just some of the housekeeping stuff I wanted to do. So what we're going to do then for this class is we're going to get into the other part of integration by parts, which is tabular integration. It's something that I haven't really taught in the past, and part of the reason was, I guess I never learned it when I was in high school, but what kind of happened over the years, this is my 4th year at ISM, my students, there were always a couple of students every year that would still just do it whenever we would have an exam. And once I started paying more attention to it, I realized that it was actually very useful. And so what I'm going to do is I'm going to demonstrate to you first how to do a question without tabular integration, but then once I demonstrate what we do, I think you'll realize then that it's actually very beneficial and you would want to use it as well. So the first thing is getting to a question where we can use tabular integration, but I'm going to pretend that I'm just going to say we're not going to do it initially. So from yesterday with integration by parts or from UVDOV, we knew that we had to start by identifying a U, and we had to also identify a dv for this. So first, what should we let U be and what should dv be in this integral?
dv is e to the x.
All right, good, yep. And we should include dx there. So that means then that U has to be x squared. Now that we've identified those, we can then go ahead and figure out du is dx, v is just e to the x as well. Okay, now that we have that, we can go ahead and do our integration by parts. So remember, well, that's a bad v there. So of dov tells us that we're going to do x squared times e to the x minus, and now we're going to have the integral of duv, so that is going to be 2x e to the x, and then dx. Now we have a problem, which is that this integral still cannot be solved. So we need to do integration by parts a second time. So once again, we're going to have a u, a du, a v, and a dv. We start with u and dv again. By the way, this is a case where you don't want to be switching what you used for u and dv. Don't put e to the x there. Do not put 2x dx there. Because what's going to happen is you're just going to undo all your work from the first step, and you're going to get back to the original integral, and that's not helpful. So you need to be continuing with the same functions that you used for the first step as well. So if your du up here became 2x, then your u should be 2x. And if you used e to the x for dv, then whatever became v should become your dv down below. Now we can integrate both of these, or sorry, not integrate both, but we'll integrate dv to get e to the x. We'll find the derivative of 2x, which is 2 dx. And so then we will get x squared e to the x, because that was from the beginning. And now with the minus, we have to be careful. We need to put our next thing in parentheses, because remember, the of dov that we're about to do represents this whole integral there. And if we're subtracting the entire integral, that means we have to subtract our result from of dov as well. So we're going to get 2x e to the x minus the integral. And then duv is going to be 2 e to the x dx. And now we are at a point, this integral we can solve without needing integration by parts. So I'm going to go ahead and simplify the rest of this. We have x squared e to the x minus 2x e to the x. And then notice, oh, that doesn't want to write there. Yeah, good enough. Notice then we've got subtracting, we got two of them there, so we're going to have to turn that into plus. And then the antiderivative for 2e to the x is just 2e to the x. And then finally, plus c at the end. And so that is our answer for this integral. So the work for this wasn't really too bad. However, there's an even faster way in order to solve a problem like this, and that is tabular integration. So I'm going to go ahead then and show you how we can get the exact same answer using the other method. So you honestly could actually use tabular integration for any question for integration by parts, but it's especially useful when you know that you're going to need to integrate multiple times, and it speeds up the process a lot. So what we're going to do is we're going to make this table here on the left side. And since we know we're going to have to do integration by parts multiple times, we're just going to find our, and I labeled it f of x and g prime of x, I guess just to copy what the Thomas book did. But if you wanted, you could just say, oh, well, that first one is u, and then the second one is dv. You could do that as well. So what we're going to do is we're going to start with our f of x, or our u, which we identified before as being x squared. And we had identified our dv as being e to the x. Then what we're going to do is we are just going to find all the derivatives of x squared until we can't find any more. And then we're going to find all of the antiderivatives. I'm not writing very well. We're going to find all the antiderivatives of e to the x. And although e to the x goes on infinitely, we know to stop when we can no longer find a new derivative for x squared. So we'll go ahead then and find those. So for x squared, we know it's going to go 2x. Then it's going to go to 2. And then we get to 0. And we know that we don't need to go past 0 because it's just going to keep being 0 over and over again. So we know to stop there. Then I'm going to go ahead and find all the antiderivatives for e to the x. E to the x, e to the x, e to the x. And remember that when we were doing of dove earlier, fix that v again. So here's our u. This was originally dv. That one right there, the second e to the x is v. So the first part of our answer is going to be found by multiplying those two together. So I know to start with x squared e to the x in my answer. And here's what's going to happen now. So I'm going to erase these. I'm going to draw a line connecting those two. And the first part is always positive. So I'm going to mark a plus sign just so I remember that, okay, I'm going to mark that that was positive. Now the second part is found by doing 2x times e to the x. And we have this minus sign here. So that means that that had to be negative. So we're going to subtract that part. And then we have to do 2 times e to the x. And if you remember from the first time that I did this, what happened, let me take this and rewrite it. When we did it a second time, it became uv minus integral duv. I'm taking some liberties. Obviously, these u's and v's are not all supposed to be identical. But what happened then for that next part was that we had to subtract a negative. So that means then that we're going to get a positive. We have to add 2e to the x. And we don't have anything else because the next one would have been 0 times e to the x, which is just 0. So we're done. And there is the full antiderivative. And if we go back to what we had before, look at that. We have the exact same answer. So once you start getting the hang of tabular integration, it's going to be much faster because all you need to do is you just have to find the derivatives of your u, find your antiderivatives of dv, and then you just have to go down diagonally while alternating addition and subtraction, and that will get you your answer. So are there any questions so far with what I've done here?
Yes, Mr. Chris, I have a question.
Yeah, what's up?
So, what if we have like sine square and the derivative of that is like being ugly? Should we still use the tabular integration?
So like if you had, so you're saying like if you had sine squared over here?
It doesn't matter, something ugly.
Yeah,
That has
so
like cosine inside and like square roots and stuff.
yeah, so it is possible that you might get some questions like that. Now remember that we want our f of x or our u function to be something that we can easily find the derivative of. and we hope that we can get it to be like this. Hopefully we can get it to 0 at some point with enough derivatives. Yeah, because the first derivative of sine squared is 2 sine cosine. And then the derivative after that is getting into 2 times, if I recall correctly, I believe it's 2 times cosine squared minus sine squared. And that's never going to get easier. So in that case, integration by parts doesn't look very helpful for us. If you all look in the Thomas book, actually, I think all the questions, though, are usually pretty, I don't want to say simple, but I guess like usually most of the questions are written so it's pretty clear to see what should be a U and what should be a DV, and they're usually not too complicated. So Miriam, your question about what about like having a sine squared, I think that would be I don't think that would usually show up for integration by parts. I don't think we would usually multiply something with sine squared.
Okay, got it. And
Yep.
one more question. So
Yep.
that's only for indefinite integrals, right? What about definite integrals? How do we solve this kind of question with
Oh yeah.
indefinite integrals
So
and
with
indefinite?
with definite integrals, we could still do the same thing. So I'm just going to say, let's pretend it goes from 0 to 2. So we can still do the tabular integration, and then what would change, or I'll use the bottom one actually. Instead of the plus c, once you've done your tabular integration and you've got this right here, then you just need to take the entire thing and just put that at the end like we usually do for a definite integral, and then you can just put in 2 and 0 to finish solving it.
Okay, got it.
Yep. All right, any other questions from anybody? No? Okay.
Oh wait, I actually have one. Sorry. Okay.
Yeah, no problem.
So if you want like another time, say like you need like an extra step, like from like x squared to get to 0, or I don't know, just like any other number that would take an extra step, but you still had e to the x, you know?
Mm-hmm.
Like would the next one after like uv minus parentheses uv minus integral of duv, right? Would the
Yeah.
next one be uv minus, wait, what would the next step be? Or would we ever really have to know that?
Oh, so I think I understand what you're saying. What's going to happen is that you're just always alternating positives and negatives here. So it just continuously keeps going like that. The next one I think, oh, that only has 2. Do I have one? Oh yeah. So Jamez, this might be like what you're asking. Because now we've got the x cubed. So
Oh,
this time we're actually going to have to do it one more time than the previous example.
okay.
And you would just keep on going, and you just make sure that your pluses and minuses are alternating every single time. And you just start with addition the first time.
Okay.
Yep. Okay. So if everyone's okay with it, then I'm going to move on to the next one. So here's another example. We're going to use tabular integration. I'm not going to show how to do it the long way. So now I think it's coincidental that most of these examples have had dv second and v first. I don't want you to get in the habit, or I'm sorry, not v, but you. I don't want you getting in the habit just assuming that's how it's going to be every single time. Actually go through the process of thinking, okay, which one of these has a number of derivatives that I can find that eventually goes to 0, and which one has an antiderivative that is pretty simple to calculate. It just so happens, though, that in this case, yes, our u function does end up being x squared minus 2x plus 1. Yes, our dv does end up being e to the 2x. Okay, so we're going to go ahead and set this up like I already told you, the first part would be x squared minus 2x plus 1. And then for the second part, we're going to get e to the 2x. So over on the left, we have to find the derivatives. On the right, we have to find the antiderivatives. So these derivatives, not too bad. We got 2x minus 2. And then we get 2. And then we get 0. And once we get 0, we know that's where we can stop with our antiderivatives. And then over on the right side, so I know we've kind of been struggling a little bit with this. So just as a reminder off to the side here, if we let u be 2x and we let du be 2dx, then we need to put in a 2, which means we need a 1/2 outside. And what happens with this is that we get 1/2 e to the 2x. And then I guess plus c. But therefore, our antiderivative is going to be that right there. So this is how I know that it's going to be e to the 2x over 2. And we just need to divide by 2 every single time. That's the derivative of the exponent. So then the next one is going to be e to the 2x over 4. The next one is going to be e to the 2x over 8. Okay, and then we need to go diagonally. And we alternate positives and negatives. And I'm going to erase all this here. So our answer should look like this. We're going to have x squared minus 2x plus 1 times e to the 2x over 2. Then we have to do minus, and it's going to be 2x minus 2 times e to the 2x over 4. And I kind of, actually, I'm going to do this on the bottom because I'm running out of space here. And then the last part is we have to add, and that says 2 times e to the 2x over 8 and plus c. And that is the antiderivative. So are there any questions then with how I got this? No? Okay. Is it okay for me to move on then?
Yes.
Yeah. Okay. So what I want you to do then, spend a couple minutes. Oh, yeah. Okay. Sorry. Just want to make sure that I knew where I was at. Okay. So go ahead then. I want you to try this one. This is going to have one additional step compared to the prior two. So spend a couple minutes on it. I don't know if it's going to be easy to type this in the chat, but I'll just give you a couple minutes and then I'll show you how to do it. Oh, I should say, if you have any questions or if you need a hint, just let me know in the chat and I can put it there. Okay, so this is what you should have done in order to get this. So x cubed is going to be our f of x function. So x cubed, 3x squared, 6x, 6, and then 0. So that's where we're going to stop. And then for g prime, that's going to be sine of x. And I knew that sine of x couldn't be f because that was just going to go on forever with its derivatives. So then we're going to get negative cosine of x. We're going to get negative sine of x. Then we're going to get cosine of x. And then finally, we get back to sine. Then we have to go diagonally. Remember, we're alternating pluses and minuses. And then this one's going to be a little trickier because now we've got some negatives thrown in as well. So we're going to have to be really careful when we're doing this. Plus, minus, plus, minus. So the first one is actually negative x cubed cosine of x. Then the next one is plus 3x squared sine x. Then we have plus 6x cosine x.
Mr. Bruce, the derivative of negative sine is negative cosine.
But remember, we're doing antiderivatives here for g of x, or g prime, I mean.
So it's derivative for f of x and antiderivative for g prime of x?
Correct. And then the last part is minus 6 sine x, and then plus c. So that should have been your antiderivative. There you go. Any questions with this?
If we could get plus C on an FRQ, how many points are they going to take off?
What I've seen is usually the plus C occurs. Well, okay. So here's the complicated thing, is that usually in a scoring rubric they require. Usually they say it's only 1 point, but the problem is that it usually ends up being on a differential equation question where it's like it's like dy over dx equals, I don't know, I'm just going to say e to the x y. And usually these questions end up being worth 5 or 6 points. And then even though the plus C is 1 point on its own, they usually put in a special note saying no additional points can be earned if plus C is forgotten, which usually means then that you only get like 3 out of 5 or 3 out of 6. So sorry, Jamez, that's a really long way of saying it's technically just 1 point, but usually those questions, or usually the questions that involve the plus C are the ones where you actually get penalized 2 or 3 points for forgetting it.
Okay.
Yeah. So, but usually most FRQs do not require plus C. Usually usually the College Board is more interested in asking you a definite integral as a FRQ.
Okay.
Yep. Okay, so the last one. Oh, I think you all are gonna hate this so much. the good news is that there's actually a very clever way of solving this.
Yes, just not doing it.
Can we? Do you say can we just not do it?
Yes, that's the smart way of doing it.
I promise you, Mr. Geisfeld and I have never asked this type of question on a periodic. I don't know enough about the BC AP exam, so I can't speak to that. But I'm going to show you anyway, just because the answer is quite clever. And if some of you were wondering what happens if you have to do integration by parts forever, well, this is what's going to happen. So
will the 2's cancel something?
We're not quite cancel, but we are going to get we're actually going to get some terms that will be identical. So not, and I know you're kind of wondering, how doesn't that mean that they cancel? No, we don't get a positive and a negative of them. We're actually going to get two positives, and we're going to be able to combine them. So what's going to happen, unfortunately, tabular integration is not possible for this type of question, because like in this down here, tabular integration, there's no integrals in the entire answer, which, I mean, that's what we're trying to get. But in this type of question, this is going to sound really strange. We actually want to keep the integral in the answer. And as I go through it, you're going to start to see why. So what we're going to do is we're going to start with integration by parts like we usually do. And looking at this, well, I'm sure, I mean, this is the whole point of why we're doing the question in this way anyway. It kind of doesn't matter what we pick for U and DV, because either way, it's just going to keep going on forever. So I think what I'm going to do is I'm just going to say U be e to the negative 2x. Yeah, I mean, it doesn't matter, I suppose. And I'm going to let dv be sine of 2x dx. So the du is going to be negative 2e to the negative 2x dx. And then the v is going to be negative cosine of 2x over 2. And what we're going to do then is we're going to set up our of-dov. So we're going to get uv is negative e to the negative 2x times cosine of 2x all over 2 minus duv. So that's going to become positive 2e to the negative 2x cosine of 2x over 2, and then dx there. So yeah, this is not looking fun already. It's not getting any easier for us. So the next part then is, just to make it easier, I'm going to take out this 2. I'm going to move it outside of the integral. Is it okay if I did it like that, or do you want me to write another line?
Yes, fine.
Wait, Mr. Best, can't you like cancel the 2's? Like simplify the 2's?
Oh, duh. Yeah, you're right. Duh. Thank you. There we go. That takes care of one issue that we had. Okay, thanks. So now we're going to have to do integration by parts a second time. So once again, u du v dv. Reminder, whatever you used for du in the first Integration by parts, you need to use that as your u in the second one. Now, granted, we've canceled the 2, so it's actually not exactly the same. But regardless, e to the negative 2x should stay as our u, and dv should continue to be the trig function. So there's cosine of 2x over there, and whoops, dx. So then v is going to become sine of 2x over 2. And then we, once again, are going to have negative, derivative, sorry, negative 2 e to the negative 2x. And maybe just, I'll start changing some of the colors here so it's a little easier to tell them apart. Okay. So the first part drops down. We got negative e to the negative 2x cosine of 2x over 2. Minus, we need parentheses. We have to do of again. So this time we are going to get e to the negative 2x sine of 2x over 2 minus the integral of duv, which is going to be negative 2 e to the negative 2x sine of 2x I'm running out of space here, all over 2, and there's supposed to be a dx. I'm going to have to cram in there somehow. There we go. Okay, at least for this second part, once again, we're going to get those 2's to cancel. And I'm going to take this and I'm going to rewrite it, just taking care of those negatives. And let's see, we got to be careful now. This is going to be 2 negatives make it a positive. We're still going to be subtracting, so it's minus the integral of e to the negative 2x sine of 2x dx. Okay, now, if you have glanced back at what the beginning was for our question, oh, that does not want to stay, does it? If you've glanced back at what we started with, you're going to notice, and once I've got this dx, I'll show you, I'll zoom out and I'll show you. We are back to what we just started with. That integral right there is exactly the same as what we started with, and that looks bad. It like it says up at the top, it's going to cycle forever. Here's where we have good news, believe it or not. We haven't done this before, but technically this is what we should have been doing every single time we answer one of these questions. Our antiderivative is equal to the thing that we started with. So if it was e to the negative 2x sine of 2x dx up here, then it should have been that here, and it should have been that here as well.
So it cancels out. They cancel. No.
Not quite canceled, but
yeah, it's times
but
2.
there's 2 of them.
Integral.
So what happens is that we can add the integral to both sides of our equation. We're gonna cancel that one by adding it over to the left side. Sorry, I'm getting really sloppy here. e to the negative 2x sine of 2x dx. Now we've got two of the integrals over on the left side. And you can see that the result is going to be that we just have to divide both sides by 2, and we finally have an answer for this. And so then we end with the original integral equals 1/2 of this right here. Sorry, I'm getting lazy. I'm just going to copy and paste it now. And technically, geez, I'm running out of space. I need to shrink this down. Technically, we need a plus c there as well. So I need to fit that in once I'm done. There we go. And so that, here, I'll zoom out so you can see the entire question there. Oops. There we go. Okay. So there is the answer. So I just wanted to show you this question. Just in case you were wondering what happens if integration by parts needs to be done infinitely. I probably scrambled your brains with that, so I'm not going to have you worry about that one down there. I'll finish off the notes. I'll put it on Schoology so you can see it there. We'll have the video so you can look back at this anyway. So that's going to be everything. Oh, I forgot to mark that. Okay, so the assignment here, I'm going to say 3 is optional. So really all you have to do is just get 17 and 22 done. Warning you, 22 is just like the last question we did, so just be aware of that. But 17, 3 and 17 are ones that you can use tabular integration to solve. So that is everything, everybody. Yeah, what's up? Everybody else can head out if you want.
Mr. Riss,